Hi! We already met FPGA devices, but we have not seen yet how they are programmed and what they are made of. Let us now get a little bit more into this. As we know, FPGAs are a particular family of integrated circuits intended for custom hardware implementation, with the key property of being able of being configured after having been manufactured for an infinite number of times. Just to remind you, configuring an FPGA means changing its functionality to support a new application, and it is equal of having some new pieces of hardware mapped on the FPGA chip, having to implement a completely new functionality. This flexibility has determined the popularity of FPGA devices in a broad range of fields. I'm now going to briefly discuss the distinctive features of FPGAs. In particular, I will clarify how they can implement custom hardware via their reconfiguration. We know that there are several companies producing FPGAs, but the devices we are going to focus the majority of our examples throughout this course are the ones manufactured by Xilinx. Within this context, the following architectural details, even if they can be generally applied to other different devices, apply to the chips produced by Xilinx. The three main building blocks of an FPGA are configurable logic blocks, input-output blocks, and last but not least, communication resources. Configurable logic blocks, also known as CLBs, are the main component of an FPGA. These elements are the ones that are going to be configured to implement our logic. CLBs can be used to implement either combinational and sequential logic. In Xilinx FPGAs, a single CLB is a hierarchical structure composed by a set of slices that are, at the same time, composed by a set of lookup tables. The number of slices can vary according to the device, but in general CLB contains a set of 2 slices, which is the case for the Virtex C, Virtex 5 or the 7 series, while 4 slices were present in the Virtex 2 Pro and Virtex 4 devices. A slice, in turn, contains 2 lookup tables and the necessary interconnect hardware. The lookup tables are elements that can be used to implement, in general, 4 input to 1 output functions. Newest FPGA, like the Xilinx 7 series, are composed by lookup tables that can be used to implement functions characterized by 6 inputs and 2 outputs. Within this context, configuring a lookup table means to properly store the necessary sequence of zeros and ones in the 16 memory cells, according to the desired function. Each line is then connected to a multiplexer, which is used to read the output of the function we are looking for by connecting the desired memory cell via the proper configuration of the multiplexer, set by reading the A, B, C, D inputs to the output signal of the lookup table. The input-output block, or IOBs, have the function of interconnecting the signals of the internal logic to an output pin of the FPGA package. There is one and only one IOB for every IO pin of the chip package. The IOBs have their own configuration memory, storing the voltage standards to which the pin must comply and configuring the direction of the communication on it, making it possible to establish monodirectional links in either way, also bidirectional ones. Finally, the interconnection resources within an FPGA allow the arbitrary connection of CLBs and IOBs. The main modes of interconnection are direct and segmented. Direct interconnection is made of groups of connection that cross the devices in all its dimensions. Logic blocks put data on the most suitable channel according to data destination. This implementation usually includes some additional short-range connection that link nearby blocks. On the other hand, segmented interconnection is based on lines that can be interconnected using programmable switch boxes. Also, in this kind of interconnection, there are lines that cross the entire device, in order to maximize the speed of communication and limit the signal skew. The building blocks presented so far interconnect together in the device to create a communication infrastructure composed of the communication lines and IOBs around a bidimensional array of CLBs, which covers most of the available die area and represents the true FPGA building block. But what does it mean to configure an FPGA? How all these elements are going to be used to implement a desired system? Let us try to find out more. The memory cells attached to every configurable resources control its key features in such a way that the I/O voltage standards of an IOB are controlled by particular values in its corresponding memory cell. The interconnection among the communication infrastructure are controlled by setting appropriate bits in the configuration memory, and the equation in the lookup tables are controlled in the same way. All of this configuration memory is made of SRAM memory elements, and it's therefore volatile. When the device is power cycled, all of its configurations is lost, and it must be started afresh with a new configuration. Usually, an external machine downloads the configuration on the FPGA via one of its configuration interfaces and sends a source command to signal that the configuration has taken place. Some boards also offer a ROM where configuration is stored, so that it can be subsequently downloaded on the FPGA on power-up. A different solution with respect to the external machine, as we know, is represented by the configuration controlled by an internal component. In such a scenario, the configuration memory is accessed by the internal configuration access port, or ICAP. The file that stores the information that is copied over the configuration SRAM memory of the FPGA is called bitstream and can be either full or partial, according to the extent of configuration memory addressed in it. Just an extra note before closing this bird's eye view on FPGA resources. Nowadays, FPGAs are not composed only by the three presented building blocks, but they have additional resources directly embedded on the die. Such resources are, as an example, RAM cells, processors, DSPs, multipliers, and so on. In this way, system designers can take advantage of hardware already present on the chip and integrate in their designs without the need of having to implement all of the desired functionalities on the configurable resources, but instead exploiting the speed and the functions of pre-made embedded hardware cores. Thus, the hard cores on an FPGA enrich its functionalities and improve the overall speed of architectures that make use of them.